Alrighty, welcome back to some fun maths. Today we are looking at position and average velocity. Now in particular, if we're talking about a position of an object, generally we start at the origin, denoted by O, and if we consider straight line motion, going in a positive direction we're moving to the right, and moving to the negative direction we're moving to the left. If we want to go a little bit further in this particular case, you can see here at the start, at time equals 0, okay, the position might be at X, yeah, but it hasn't moved at 0, it hasn't moved to left or right, it's at position 0. After a certain amount of time, it could move to the position 6.25, which is to the right of the origin. And so you might see it like after time equals 5, so after 5 seconds, it's at this particular position. Likewise, from there, after 8 seconds from the start, it might be now at the position negative 8.96. Yep. Now, if we consider that type of thing going on, that can be sketched in a position time graph. So if we think about a position time graph, it would look something like that there. So you can see at time equals 0, the particle starts from rest and moves to the right, and at time equals 5, the particle stops and it changes back in the opposite direction as shown here. One of the things that you need to know is how to calculate the average velocity. Now to do this, there is a formula. It's just the change in position divided by the change in time, or the time elapsed. So again, if you consider the following that we had at the start, based on the moving particle we just spoke about, if you are asked to calculate the average velocity between the times 0 and 5, what you would do is you would look at what the change in position is from at 5 seconds to from the start. So the change in position would be 6.25, take away the 0, so there's a change of 6.25, and obviously the time elapsed between 0 and 5 is 5 seconds. Yep, so this one, take away this one here. You can get the average velocity in this particular case as being 1.25 meters per second. Perfect. If you're asked to calculate the average velocity, for example, between 5 seconds and 8 seconds, obviously we need to find the change in position and then the change in time between each of those. So again, to calculate the change in position, you would do this one here, which is negative 8.96, take away the 6.25, that would tell you the change there. And that's going to be divided by the change in time. So change in time would be 8, take away the 5, which is the 3. In this case, you would get negative 5.07 meters per second as being the average velocity. So here is an example where we do this type of calculation. So we've got an equation, 6t take away t squared is going to be the position function of a particle moving in a straight line, where t is in seconds and s is in meters. It says here, find the average velocity for the time interval between 0 and 1. So what we need to do is find out what's going on when time is equal to 0. So we can plug 0 into the equation and we can find out what is happening there. So doing that, when we substitute in 0, obviously this evaluates to 0. Perfect. We need to find out what's going on when the time is equal to 1. Plug that into the equation. 6 times 1, take away 1 squared, we get it is equal to 5. So again, you now know the positions, so you can calculate the change in position between each of those. So from the 5, take away the 0, so the change in position is going to be 5, divided by the change in time. So in this particular case, going from 1 second, or from 0 seconds to 1 second, 1 take away the 0 is going to be 1 second, so it's divided by 1. We can get that calculation here. The average velocity between 0 and 1 second as time is 5 meters per second. We can do the same thing again for the time interval between 6 and 8 seconds. So again, finding out what's happening when time equals 6, we plug that into the equation. We can get how many meters it is. So in that particular case, when it's at 6, time is 6, it evaluates to 0. And when we substitute in 8 as the time, obviously here we're going to get 6 times 8, take away 8 squared, that is negative 16. So again, to calculate the average velocity, it's going to be the change in position. So negative 16, take away the 0, which is negative 16, divided by the time elapsed, so between 6 seconds and 8 seconds, that's obviously 2 seconds there. So negative 16 divided by 2 is negative 8. So we can say the average velocity between 6 and 8 seconds is negative 8 meters per second. Alrighty, we're now going to look at what are called velocity time graphs. So again, we're going to look at velocity time graphs, and they're obtained from the position time graph. And each of the position time graphs is the graph of a piecewise defined function or a hybrid function where each of the components is linear. So this one here, it says the graph shown is the position time graph for a bicycle trip of a boy who lives on a long straight road. Perfect. It turns out the road runs north to south, and north is chosen to be the positive direction. Okay, so up here, positive direction, that's north. Obviously, that should be an N. No, imagine that's north, and this one here is south down that way. That's south down this way. It says describe his trip. Alright, so what you would talk about is what's happening for the first 2 hours. Okay, so for the first 2 hours, you can see he's heading in a positive direction, which means he's heading north. Yep. To then talk about his velocity, we're going to work out the gradient of that particular line. So again, we're looking at the change in position divided by the change in time. Yep. So you change from going from 0 to 20. So we can find out what the difference is there. So 20 take away the 0. Divided by the change in time is going to be 2 take away the 0, which is 2. I'm running that calculation, which is the gradient of that particular piecewise section, is 10 kilometers per hour. From here, from 2 hours to 4 hours, we can talk about what is going on. So this is another 2 hours in time from here to here. And once we talk about that, we can see that he's now changed directions. He's heading in a negative direction, so he's heading south. And he does that for 2 hours, between 2 hours and the 4 hour mark. Again, you can calculate his velocity for that particular period. It's obviously going to be the change in position divided by the change in time. So he's gone obviously from positive 20 to negative 10. So the difference here, negative 10 take away the 20 divided by the change in time from 2 to 4, that's 2 hours. His velocity for that period is negative 15 kilometers per hour. Last bit we can talk about is this last hour. And again, you can see he changes direction. He's going back in a positive direction, so he's heading north. And he does that for 1 hour. And to work out the velocity at that particular point, you are working out the gradient of that slope there. Again, change in position. So he's going from negative 10 back to 0. So 0 take away negative 10, which is the same as 0 plus 10, divided by the change in time. So the change in time from 4 to 5 is 1 hour. That comes out to 10 kilometers per hour. So that's just really describing what we see there. Next, you can draw the corresponding velocity time graph. And the good news is we already sort of worked out the velocity at each of those particular points. And so we can easily create that. So here, for the velocity time graph, we can, as we said here in the description above, for the first 2 hours, he was going at 10 kilometers per hour. So we can draw here 10 kilometers an hour. for the next 2 hours, so from 2 to 4 hours, he's going at negative 15 kilometers an hour. So again, we can draw the velocity there. Last but not least, he returns home from the 4 to 5 hour mark, and he's going at 10 kilometers an hour. You can put that velocity on there, which is pretty cool. Alrighty, next thing I want to have a chat about. Oh, cool. It's a particle question again. It says here, a particle is moving in a straight line. It was initially at rest at point O. And it says it moves to the right of the origin, or O, with a constant velocity. And it reaches a point A, which is 15 meters from O, after 5 seconds. It then returns back to O, and it says that trip takes 10 seconds. It stops at O. On the axis, on one set of axes, draw the position and time graph, and then also draw the velocity time graph for the motion. So we're going to do 2 graphs on one. So we know that it starts at the origin here, and it moves to the right of the origin, which is in a positive direction, at a constant velocity, and reaches a point 15 meters from O. So here obviously is 15 meters, but the other part is it happens after 5 seconds. So you can see after 5 seconds it's 15 meters away from the origin. So we can draw that there on the position time graph. Next, it returns back to the origin from this point. It's going to take 10 seconds. So from 5 second mark where we're at, another 10 seconds is going to be 15 seconds, and it's returning back to the origin here, which is at 0 meters away. Yep. So we've drawn there that particular position time graph. Again, you can calculate the gradients of each of these sections to work out what's going on with the velocity time graph. So here again, you've got a change in the position from 15 to 0, and you've got a change in the time from 0 to 5. Running the calculation, you get the meters per second velocity as being 3. From this position here to the time 15, we're looking at the gradient, and again, change in position divided by the change in time, you will get negative 1.5, and they've put that on there with the little blue dotted line. Alrighty, last thing is what we call the instantaneous velocity. It says here instantaneous velocity is the instantaneous rate of change in position with respect to time, and it can be thought of as the gradient of a tangent to the position time graph at a particular point. So let's have a look at an example here to illustrate this. It says the position of a particle moving in a straight line is given by the function t cubed take away 6t squared, and we've got that there for values of time greater than or equal to 0. Perfect. Also, they've got the corresponding velocity time graph is also shown, which is great, and it says the function describing the velocity is 3t squared take away 12t. Perfect, they've got that there. First parts of these questions they're asking us to answer are to find the average velocity of the particles for each of these intervals. So they're saying find it between 3.5 and 4.5. So what you would need to do is you're going to substitute this value into the equation, take away this substituted value in the equation, divided by, as we've said, the change in time, and we can run that particular calculation. Now the change in time in this case is obviously the difference between 4.5 and 3.5. So the change in time, the difference between that, take away that, is 1, which is where that comes from. We can run the calculation, we get the average velocity is 0.25. This one here, again, to work out the average velocity, we're going to substitute this into the equation, take away this substitute into the equation, divided by the change in time. The change in time between that and that, 4.1, take away the 3.9 is the 0.2. We can get that calculation here. Last but not least, again, no surprises, we're substituting in this into the equation, take away this into the equation, divided by the difference in these, which is that one, take away that one is 0.02. Again, we can calculate that. Happy days. Tick. Next it says from part A, what is the instantaneous velocity when time is equal to 4? So for this one, you want to be looking at the velocity time graph. and you can see here at time equals 4, the velocity is 0. Okay, so we can just suggest there that yeah, the velocity is 0. Last but not least, it's saying, hey, for what values of t is the velocity positive, and then also for what values of t is the velocity negative. Okay, what we're going to be looking at here is this graph here, the velocity time graph. You can see these values are negative here on this graph. Between 0 and 4, these are all negative values. So you can say, obviously, I'm answering this one here. For what values of t is the velocity negative? It's negative between 0 and 4, which was part 2. On the other hand, you can look here at the graph and see where it's positive. It's positive in this section, so greater than 4 is where it's positive. Alright, thank you very much for listening up. I hope you have a good day. Bye for now.